almost always turn out by most people to be UFOs. They don't understand what they see. And furthermore, it's not just that they're UFO. UFO means unidentified flying object. It was a phrase or an acronym coined in the early 1950s to explain something that was unexplained in the sky, but it has become to mean, that is, an unknown means an alien spacecraft. Today, people, when they see lights in the sky, do some very bizarre things. It changes their lives. People quit their jobs and devote themselves to UFOs. And this is more than just a few people doing this today. There's a very famous doctor in Phoenix during the Phoenix Lights who quit her practice and started making UFO movies over the Phoenix Lights. Now, what are lights in the sky? By and large, for most people, when they go out and see lights in the sky, they're misidentified, misinterpreting, misperceiving, misjudging, misunderstanding, and unfortunately their whole belief system is overriding all of this, so automatically it becomes an alien spacecraft. Now, a little quick thing about me. Yes, I was a bit younger here. I am a retired Air Force pilot and an astronomer. I held a top secret SCI security clearance, which is somewhat relevant to today's talk. I have worked and flown in Area 51. I have it in quotation marks because the Air Force has never called it Area 51, ever. It's called something else that's classified. So I'm speaking only for myself because the Air Force is very sensitive about this subject. They don't want anybody to talk about it, and since I am a retired officer, I always put that disclaimer in there. I have observed the sky. I've got over 40,000 logged hours of observing the night sky, thousands flying, thousands observing the sun, thousands observing atmospheric phenomena, and in addition, I've logged over 3,000 parachute jumps. As you see, the sky has been a big part of my life. This is some of the things I've seen. Thousands of fireballs, and we'll get into what that is later. Hundreds of satellite boosters and reentries. Hundreds of different types of mirages. Atmospheric lensing. Flares. Ball lightning. St. Elmo's fire. Dozens of skyhook balloons. And yes, I have actually been struck 7 times by lightning. Now, some people say that explains the way I am, but I will let you be the judge of that. Reports. When you have the public reporting lights in the sky, typically you have 3 categories here: the honest report, the exaggerated report, and the hoaxed report. The honest report is someone who honestly is trying to explain what they saw, but they're almost always wrong. It's just so easy for people not to understand what they're seeing, having their overriding psychological and sociological issues influencing what they're seeing, their lack of knowledge, particularly of astronomy and angles. You'll typically see people say, it was moving 3,000 miles an hour, it was a mile in diameter, and it's a mile away. Now, none of those are knowable. You can't possibly know that. They're just making it up because it's what they think it should be. And they're reporting totally out of context. And of course, a lot of times when something pops up, it surprises people, and that influences how they see something, particularly if it's something they've never seen before. Now, of course, you have the exaggerated report where somebody at this point is trying to throw their opinion in there and exaggerate what they actually saw. Again, it's very inaccurate. It's an embellishment. It's not technically a lie. It's more of a tall tale. And then, of course, you have the hoaxes. They're just lying. And today, most hoaxes are actually created in Photoshop and After Effects. Unlike in many years past. But the ones that are actually in the sky tend to be road flares hung from helium balloons. This is incredibly stupid and dangerous to do, but people do it all the time. Everybody knows that After Effects is the video version of Photoshop for video. Before I begin here, I'm sure all of you have heard about the end of the world on December 21st at 11:12 Universal Time. Anybody not heard about it? Does anybody think the world's going to end? It could. I mean, an unknown asteroid could pop up and hit us, but I think it's highly unlikely. What this is based on, in large part, is the winter solstice. People think about it as a day. The winter solstice is not a day. It's an exact moment in time when the sun reaches in the northern hemisphere, when it reaches its greatest southern elongation along the ecliptic. The ecliptic is the projected plane of the Earth's orbit, which is tilted 23.5 degrees. And so when it reaches that moment, that time on that day, on 21st of December in the northern hemisphere, that is actually the winter solstice. Now, this is all fairly complicated because we base our time on the sky. And that's based on the Earth's rotation, both on its axis and around the sun. And it's not consistent. It's not exactly the same all the time. And things change. The Earth wobbles on its axis in a 26,000-year period. And so what happens is the sky changes over that period of time. This is also why astrology doesn't work. And here's just some of the parameters on the Earth's orbit. You will notice here that, in fact, the closest approach to the sun is January 3rd. The furthest away from the sun is on the 4th of July, and this is the greatest elongation of the ecliptic here. And the actual orbit of the sun is, varies plus or minus about 2.5 million kilometers. So, and then you have all this kind of stuff, how we measure the year. Astronomers use this, but you can go from perihelion to perihelion or equinox to equinox. So what about the end of the world? Well, this all started about 10 or 15 years ago when some people sort of looked at the Mayan calendar and all of a sudden realized that it was going to end on December 21st. Just like our Gregorian calendar ends on December 31st. But the world doesn't end every year. So this, of course, is a bunch of nonsense. The Mayans basically had no mathematics. They could count, and that was about it. And they had this long count for their calendar, and it does indeed, if you read some of the records correctly, end on around the 21st of December. There's lots of New Age beliefs about this that have nothing to do with anything. They just want to believe the world's going to end. The galactic alignment is what I'm going to speak about a little bit here. And, of course, Planet X, there's this idea that somehow this rogue planet's going to fly through the inner solar system and disrupt the Earth. And, of course, there's no such planet. Doesn't exist. And geomagnetic reversal, this is something that could actually happen. It's not likely to happen on December 21st, but it will cause a lot of havoc, but it won't end the world. And I'm going to talk about this a little bit because of what's happening to the magnetic pole of the Earth a little bit later. But let's talk about galactic alignment. Back in 2003, when Planet X was going to come by the Earth and tilt the axes, not the magnetic axis, the real axis of the Earth, I offered this wager that if anybody wanted to sell me their property at 10 cents on the dollar, I'd be happy to buy it. Because if the world was ending, they really didn't need it. I did actually have a few people take me up on this. We can talk about their judgment, but okay, let's talk about this. This red line here, it may be a little hard to see. That is actually the ecliptic in the sky. This is a star chart from a program. This is the sun right here. And what you're seeing is the sun always moves along that line. You can't get off that line because that's a projection of the Earth's orbit as we see it. Now, where's the center of the galaxy? The center of the galaxy, this is for December 21st at 11:12 Universal Time. This is the center of the galaxy right here. It's 5.5 degrees away. So it's not lined up, so you don't have to worry about the world ending. And of course, right here is the center of the galaxy. Everybody recognize it? I took this image a few weeks ago. I'm going to have to step back here a bit. The center of the galaxy is right there. It's Sagittarius A, and there is indeed a 4.1 million solar mass black hole there, but you can't see it because there's so much dust obscuring between us and the center of the galaxy. And I want to show this as an example because there's something called a window that's about 4 or 5 degrees away from here that I took a picture of to show you an example of how much difference the dust makes. There are about 15,000 stars on this picture. It's about 3 degrees by 2 degrees wide, taken with a Canon digital single lens reflex on a astrograph. But this is only 5 degrees away. And I don't know if you notice the difference. There's 15 million stars on this picture because the dust is not obscuring it. You see some of it, the dust is in here obscuring that area. So here's the night sky. I was hoping if it was clear, but I don't think it's going to be. We'll go out, I'll talk about that later, and use some lasers and look at the night sky. By the way, how many people own one of these green lasers? How many people know how they produce their light? Physics people? What's the wavelength that this produces at? The wavelength you see over here on the wall is 5,320 angstroms, or 532 nanometers. I hate nanometers. Any rate, but what it does is it takes an infrared beam, twice that, and pulses it. Now, why is that important? It's important because if you have one of these, and it's a cheap one, it's dangerous. Not because of shining in your eyes, that's dangerous to look at. Why? Because if this doesn't have an infrared filter on it, you're looking at infrared radiation, it can damage your eye, and you will never see it. So if you have one of these, make sure it has an infrared filter in it. Okay. The sky is filled with all kinds of objects. And of course, historically, people thought of the sky as being very mysterious. All these lights in the sky, they didn't understand what they were, heavenly substances and various other things. And as a result of it, in ancient times, they viewed the sky as having gods in the sky in various forms and other ways. Today, many people sort of bridge this gap by sticking this in the middle, an alien spacecraft. So, this magical sky is very distant, and this is even to people today, untouchable, not controllable, powerful, filled with darkness and fear, and people are looking for meaning in anything. And of course, historically we had the gods and the myths, more recently astrology, and of course today UFOs and aliens. Now, very often people will talk about this idea. When I'm on television a lot, they ask about this all the time. The trained observer. Who is trained to look at the night sky, or in the daytime for that matter, and identify what is there? And what kind of training do you get for this, and what do you observe? Well, in popular culture, this is meant to be some person who's trained to look and observe accurately at the sky, and it's typically described or promoted as the idea of being pilots and police officers. And lots of people think they're incredibly credible. We have a few pilots in here. When was the last time any of you were trained to identify lights in the sky or UFOs? I know in all of my years I never had any of that training. And in fact, it turns out that police officers and pilots are some of the absolute worst observers of the sky. This has been documented in numerous studies. They cannot identify a damn thing if it's not another airplane. It's just terrible. So when you see a police officer or pilot say, "Oh, I saw that, and it was weird and unusual," don't believe it. Now, this training doesn't exist, but today I'm going to try to lead you through some of the things that I think are important about this idea. For instance, the observer needs to have some knowledge and experience of what he's looking at. He needs to be able to observe without prejudice what he's observing. He needs to be able to record accurately what he sees, and this is not trivial to do, and then evaluate the data after the fact. Now, here's some of the areas of expertise. I can't cover all of this today. But astronomical, obviously, atmospheric, aeronautical, we're going to talk about a bit. We're going to talk about a bit about visual perception, visual illusions, and I'm going to leave, I actually do have a background in psychology as well. I'm going to leave this out today because it's really all over the place when you start dealing with human beliefs and how they perceive things because of their belief system. Okay, in the astronomical arena, we're going to talk a little bit about positions in the sky, the coordinate system, the horizontal coordinate system, the equatorial coordinate system in the sky. Also, scintillation, seeing magnitude scale, meteors and fireballs, and sidereal time. And this I'm going to talk about a bit. When you look at something in the sky, you don't know what it is. All you can talk about is the angular velocity, angular direction, the angular distance, the angular diameter. Because if you don't know what it is, you can't judge any. You have to have one parameter to be able to judge the other parameters. So what you really want to do is how fast is it moving in an angular sense? And you almost never see this. People say it's moving 3,000 miles an hour. And I always say, well, how exactly which radar system in your eyeball measured that? You can't measure that. But you can say it was moving at 10 degrees per second. That you can say. So, any rate, let's talk about some of the information that we really need to talk about here. Time, universal time, we're going to talk about that a bit. Your latitude and longitude, how you get it. The brightness, I'm going to use magnitude, and I'm going to talk about why we're going to use magnitude. Altitude and azimuth in the sky. You need to take a look at what is going on in the sky from a standpoint of inversions, temperature, because this affects what you see in the sky. Angular motion, the shape, what is it? A point, many points, a solid object. The distance and size is only you can't do either of this unless you can refer it to something, and that's usually unknown. Then the proximity to MOAs, military operating areas, airways, and military bases. And astronomical, we're going to talk about how you figure out some of the things in the sky astronomically. And I'm just really not going to talk much about sociology today and a little bit about hoaxes. Okay, here's some of the tools we're going to talk about. A clinometer measures altitude, that is the angle up from the horizon. A compass measures azimuth in magnetic, not a GPS. GPSs are not compasses. We'll talk about that. GPS to get latitude and longitude. A planisphere, the easiest way to identify the constellations and the stars in the sky, and then a couple of software programs. By the way, I have a copy of each of these if you want a copy of it. This is an old DOS program that's really very good, and this is a French program that's freeware. If you want a copy of it, I have them on CD disc. I want to talk about the maps and the charts I passed out. A little bit about optics, some about cameras. How many people have a camera phone? How many people think it's really a good camera? I'm going to show you just how good it is. Talk about lasers and the value of them, and laser rangefinder is a handy tool to have. I didn't bring it with me. I should mention that some of the stuff I could have brought with me, I didn't. Turns out TSA was very interested in my bags. In fact, they broke both of my bags open and went through every single item and broke a couple of things. I didn't know about it until I opened the bag, and there's a nice note from them. So, okay. How do you measure an angle in the sky up from the horizon? Well, you have to do it in some way to measure that. Now, I should say, if you hold your arm out at arm's length, your thumb is roughly 1.5 to 2 degrees. Your fist is about 10 degrees. So if you were to stack 3 fists, you'd be 30 degrees up in the sky, but that's not terribly accurate. So what you can do is an old Boy Scout trick. Take a protractor and very carefully line it up horizontal with a piece of PVC pipe, and then put a chain or a string on it, and then do this, and then wherever it is, you pinch it off there, and you can read it right off the protractor. I'll pass that around. A better way to do this is with this device right here. I don't know of any place you can buy this except a very high-end tool store online and Harbor Freight Tools. The only place you can buy it. Home Depot, Ace, nobody sells it. What it is, it's a digital angle level. It's really designed for carpenters, but what's really nice about it is you punch the button on it, you level it, and then you do this. And it reads the exact angle on there. Now what you do is you take a tripod of some sort, or a monopod, you drill and tap a hole in this, 1/4-20, and you mount it on here. You look at your object wherever it is and just sight along it, and you read it's 19.9 degrees. Very simple. Or if something's up 30 degrees, you just move it up to 30 degrees and you can sight it. Very simple. $25 at Harbor Freight. Okay, more sophisticated, and my personal preference is this, which I won't pass around. This is made by the sort of the best compass company in the United States, I think probably in the world, Brunton. And what it is a survey master. On one end, it has a compass. On the other end, it has a clinometer. And what's really good about it is, I'll talk more about this on compasses, is you can take it and sight through the end of it, which has a 10x magnifier, and you can read it to 1/4 degree. That's magnetic. You flip it over, that's altitude. Very, very useful device. Okay, compasses. Compasses are obviously designed to measure bearings. Now you see here we have the four types of compasses really. This is sort of your base plate compass, your mirror compass, your lensatic compass, which the military uses, this verse, and of course a GPS. How does a GPS measure magnetic angles? Anybody know? It doesn't. This is GPS. You can get a compass in this, but the compass in this has nothing to do with the GPS. It's a magnetometer built into the object, into this device. And it's very easy to tell that. All you got to do is bring a battery next to it and watch the needle move. Furthermore, every time you turn this on, you have to calibrate it, the compass, by doing all kinds of gyrations with the thing before it actually points. And once it's all said and done, it's only good to about plus or minus 5 degrees. It's wonderful for latitude and longitude. It's awful as a compass. Huh? What?
A lot of phones have magnetometers.
Hey, yeah, they have magnetometers in them too, and they're just as good as this. The other problem with any compass that doesn't have a sighting on it is this. Let's take this base plate compass. Base plate compass. Okay, I want to measure a bearing with this. And so I got it in my hand here. I better get it well away from me because it's not pointing right. By the way, all compasses are very sensitive to any metal near them, so be sure that you don't have metal near it. Okay, so what you do is you hold it. Now, this compass, let me set this. Remember, all compasses are magnetic north, not true north. Okay. So that's saying that north is sort of someplace, magnetic north is sort of someplace over there. But where is it? Is it there or is it there? If you're going to use this kind of compass, what you need to do is hold it very carefully close to your body with both hands and then move to try to get that line to line up better. And that's also true if you're using a GPS magnetometer as well. Okay, GPS measures position, speed, and current time. That's all it does. Everything else you see in your GPS is something created in the device. They figure out your position, your lat long on the Earth, by time, not by distance. Every GPS satellite has an atomic clock in it. That's why their time is so good. Now, when you use a compass, it's really important that you understand a few things about it. It is magnetic, of course. It has to be stabilized. You just can't pop it out and use it. Some compasses take up to 30 seconds to stabilize. It cannot be close to anything like steel or iron because it will affect the bearing on the needle. Also, different compasses have different kinds of ways of measuring north. A true compass like this actually has a bar magnet in there. Cheap compasses just take a piece of steel and magnetize it. They're not very good if you do that. So, storage, some people don't realize this, but if you take this and store it in a steel box and come back in a couple of years, you might as well throw it away because it will affect the compass. So here's the 3 types of compasses. I'm going to pass a number of compasses around. We'll talk about how to measure it. Let me just talk about this one quickly before I pass it around. This is a mirror compass, which is way better than a base plate compass because you can actually measure a bearing by pointing it at something rather than just sort of holding this thing. And what you do is you look across this notch in the top and down at the mirror to see the bearing. By the way, most all compasses, the red needle points to magnetic north. So you look along here and you see that. Now with this type of compass, the military style compass, it has a lens here and it has a little string in front, and you line up the gap on top of the lens with where you're looking and then look down in the lens to read the magnetic bearing. So let me pass this around. By the way, the paper you can keep, the hardware I would like back. Let me take one back here. Yeah. Okay, let's talk a little bit about the equatorial coordinate system. Whoops. Uh-oh, what happened? Let me disconnect. Yeah. When you go out and look at the sky, it doesn't move exactly the way you think unless you have studied and been an amateur astronomer or astronomer. The Earth rotates on its axis in a little less than 24 hours. The axis is pointed, it's tilted 23.5 degrees. So the sky rotates that way. So let's assume that this is north here. And that 90 degrees away, this would be east, west, south. So let's say there's a star right here due east, and it's going to rise. How does it rise? A lot of people think it just goes this way. It doesn't. It rises at a 23.5 degree angle. So it never, if it's on the celestial equator, that is exactly east, it rises and it never gets overhead in the United States. You have to be north of east to rise to come through. The point that's straight overhead is the zenith. We'll talk about that more in the horizontal system. At any rate, so you need to get used to this idea that the sky rotates in this funny angle. And as it gets further and further south, take a look behind me. If you have a star back here, and that's a horizon, and it rises, what it's going to do during the course of the night is track like this across the sky. And a lot of people see this and they don't understand it because, oh, that can't be a star because it's not moving right. Well, as you can see here, this is pointed towards the North Celestial Pole. Polaris, the North Star, is about 3/4 of a degree away from that. So it's pretty close if you look at Polaris. But you can see here that this is the summer solstice where the sun rises and sets. The equinox, the sun rises on the celestial equator due east like this. In the winter, it rises like this, and of course, this is what causes the seasons. Now, so if you look at the North Star, now this is where the North Star, now this is distorted because of the roof. If you look up there, the laser, that's 36 degrees, which is the latitude of Las Vegas, and that's where the North Star would be. Now it's distorted, it looks higher than it is because of the roof in here. But if you were to put the stars up there with it, they don't rotate like this because you're looking at the pole. They rotate this way around the pole. And of course, if you go to the opposite, they rotate more like this around that pole. Yeah. And of course, you can have stars do all kinds of things here if you have the right diffraction grading. Now, when I pass out these planispheres in a second, I want you to take a look at the fact that the planisphere is set up around the North Celestial Pole. Now, the horizontal coordinate system, this is why I passed out the compasses. In the horizontal coordinate system, let me back up here. In this system, we measure the sky in what is known as right ascension and declination. It's sort of like projecting latitude and longitude into the sky from your position. In the horizontal coordinate system, we measure from true north, around the horizon, back to true north, 360 degrees. True north is both 0 degrees and 360 degrees. We measure up from the horizon altitude, from the horizon towards the zenith. That's the point straight over your head at 90 degrees. So it's 0 to 90 degrees here. So you have two coordinates. You have an altitude, let's say, of 30 degrees. You have an azimuth of 67 degrees. That puts your object right there, and that's how you know where it is. So the same thing applies here to this idea of angular measurement. So let's say you have an object you see in the sky, and it does that and disappears. Then that angle there is about 30 degrees from where you're sitting, and it's moving about 1 degree in 1 second, so it's moving 30 degrees a second. And so that's how you measure angular velocity. The distance would be 30 degrees across there. The direction, in this case, is, what direction is this? And nobody knows? Well, that back there is true north. This is true south. So this is east, this is west. Okay, there will be a quiz afterwards. How many people have ever taken spherical trig? I bet every one of you is a physicist or astronomer. Remember, when we're talking about all this, the sky is not a flat space. It's a hemisphere. And so when you're talking about angles and stuff, it doesn't make much difference on these small angles. If you're doing something larger, you really need to use spherical trig, and it's considerably different than normal trig. But I just thought I'd bring it up here. And then if you really want to measure orbital elements, something I do all the time, you need to know this, and this gets really complicated. So involving the inclination, and you're measuring this in relationship to the these parameters in relationship to the way the Earth is in its orbit in comparison to the ecliptic. Remember, the ecliptic is the projection of the Earth's orbit into space. Now let's talk a little bit about how you can find something. I passed out a computerized star chart that you can take a look at. Okay, what a planisphere basically does is it puts the North Celestial Pole at the center, centered on Polaris. And what you do is basically turn the ring, set the time and date, and then that's the way the sky looks at that time and date for your location. Now, one trick about this is this. You don't look at it this way, you look at it this way. And this being north, so you line it up with north, and you look at it this way, and then that's how the sky would look. Now, you can do this, but keep this pointed north. What?
It's for a particular latitude.
Yes, they're set for a particular latitude. This one is set for 40 north. Sort of pass these around and so if you take that, now you can go and look up what's in the sky that night. And if you look at the printed chart, you will notice on the printed chart tonight here in Las Vegas, you have two planets right here on here. If you look at the back side of this, it will tell you where the planets are at a particular month and what constellation they're in. Now, what you have here, of course, is the patterns of the constellations here, and we'll go into that in a second. These are just asterisms, which have nothing whatsoever to do with the stars in the sky. Nothing. They're just patterns that people make up historically, and we'll talk about that in a second. How many people have ever used a geologic survey topo map? Okay. They're a bit strange to use because they use this universal transit projection system rather than latitude and longitude. And what you see, you have a scale at the bottom, you have a date that's very important over here, you have the magnetic north and the magnetic deviation or declination, and I prefer to call it magnetic variation down here, because remember, a magnetic compass points to magnetic north, not to true north. And if you look here, you see this little diagram here, and I'll blow that up. This is what it looks like. You have true north as a star. This is grid north, because this is a projection system on a sphere, or an ellipsoid, as the Earth is. Then the grid lines on the chart are not parallel. They only deviate a little bit, but they do deviate. And then you have magnetic north. And you will notice here, this is for Tucson, Arizona, 2002. You see in 2002, magnetic north deviated 11.5 degrees from true north. And so what that means is on your compass, it's east in the case of Tucson, so you have to subtract 10 degrees from your magnetic bearing to get your true bearing to get true north. Here in Las Vegas, it's 12 degrees, and it's moving at a rate of 0.6 of a minute per year west. The magnetic pole is moving. Remember, the magnetic pole is not co-located with the rotational axis of the Earth. And this is what's happening. This is what we think the pole did before its sophisticated measurements were made. And now you see how it's moving. The magnetic pole right now is moving 60 kilometers per year. This forebodes the possibility that in sometime in the near future the magnetic poles might switch. It's happened in the past. People think it happens every 780,000 years, but there's a little uncertainty there. But you can see how it's moving, and because of this, you have to keep up on your current magnetic declination so you can set your compass to the right coordinate. And this is what the Earth's magnetic field looks like right now. And you can see it's not quite as neat as you would think it is. This is the magnetic field inside the Earth. The magnetic field of the Earth, of course, is generated by, at least we think it is, by a dynamo effect, by the various flows interior to the Earth, charged particles moving around, generating the field. By the way, you know your compass. The needle points north to the north magnetic pole, which of course is the south magnetic pole, but we designated it that way a long time ago, so we won't go into that. Now we're going to talk a little bit about charts. This is what's called a sectional chart for aviation. I only have a few of these. It's unlike the one you saw, the other chart I'll talk about in a second here. What's good about a sectional chart is it has, like a geologic survey chart, it has terrain on it. And you can see here mountains and doesn't look in focus up here. You see it has mountains and other things on here, but more important to that is all these lines on here. These are restricted military areas. Now, why is that important? Because the military drops flares. We're going to talk about in a second. Very bright flares in these military areas. And you will notice about right there, this is Phoenix, Arizona. About right there is where this UFO group in Phoenix would go out on various nights, usually on weekends, to look for UFOs. This particular night, back in 1997, they were out there also looking at Comet Hale-Bopp. When, looking in this direction, they saw 9 very bright lights in the sky, which of course they connected the dots and made it into a single object. And they thought it was very close. But in fact, there were A-10s out here in the military operating area that at 10 o'clock at night were going home, and they had 9 flares left, and they dumped them all at once. And these aren't your ordinary everyday flares. These flares burn at 2 million candle power. They're on a parachute, and the heat of the flare will actually suspend it. The hot air going up in the parachute, it will not descend. It'll just hang there until the flare burns up. And they burn for 2 to 3 minutes. And they're so bright that even at 150 miles, they're brighter than Venus. So they're bright. So this is what they saw out there. So how do you know this? Well, if in your local area somebody sees some bright lights, you ought to check a FAA sectional to see this. Now, this also is, I should say, this kind of thing you see around the so-called Area 51 as well. But in that case, it's a little different. You can drive a car in here. You cannot drive a car in the restricted area 4808 North. They will shoot you. And I do mean they will shoot you. No ifs, ands, or buts. So I don't recommend anybody trying to go in there. So, at any rate, I'm going to pass these sectionals around. I've got, this side will get Las Vegas, and this side will get Phoenix. But what I want you to look at is the fact that you can see where these areas are, and then you can look over here and mark where you're at, and latitude and longitude, and sort of figure out where, if you're pointing at a MOA or not. This has a big, I'll go into Stevensville here in a second. This has a totally, I picked up a sectional of that area, of that area, and it explained exactly what happened. Okay, this is that en route chart, those white publications I handed out. Again, FAA. What this shows you, this is Tucson, this is Phoenix. But what this shows you is the airways, for those who are not pilots. We generally fly in the sky, both military and civilian, along airways that are designated with points, VORs, and we fly along these routes in the sky. And then, of course, it's also marked where you have the MOAs on here as well. But it's nice to know this because in the case of the Phoenix Lights, two things happened that night. One was, at 10 o'clock, they dropped some flares out here. But before that, there were some airplanes flying in from Las Vegas, and they were sighted along this route coming into Tucson. That's because they were coming out of Las Vegas on a training mission to stay in Tucson for a few weeks to do some training. And people sighted them along the way. And if you track where they were sighted, you will see that they were exactly along this airway. Optics is always handy to have optics just to look at lights in the sky. If you have a telescope or some binoculars or a spotting scope, just be careful when you do that to realize that if it's not an expensive set of optics, it can cause issues. That is, cheaper optics experience both spherical aberration and chromatic aberration, where they distort the image, particularly when it's a point of light, and they change the color of it. Now, other things, I want to talk about cameras. In fact, I think I'll talk about the camera issue and then come back to this slide first. Okay, resolution. This is a mini version of the 1951 resolution pattern for the United States Air Force. The Air Force has done all kinds of high-tech things. In fact, if you think there's hardly a high-tech item you can think of that today wasn't funded and sponsored by the United States Air Force. People don't realize that, including CCDs and CMOS and all kinds of other things. Any rate, what I did is I took the card, set it up on my dining room table, and imaged it at 50 centimeters, half a meter, with this HTC Thunderbolt camera phone, a point-and-shoot Canon SD600, and a Canon 5D. And this is the three images here. Then I took and blew them up all the same size, and I think you can see why you don't want to use a camera phone. A camera phone is essentially a pinhole camera. Because the lens is so tiny, remember resolution, given everything else being equal, is totally dependent on the size of the aperture of the lens. And take a look at your camera phone and see if you can see how big that lens is. It's about 1 millimeter, maybe 2 millimeters. So you can see here, this is the Canon 5D. This is a blow-up of this. And you can see the resolution. You can see here, you can barely see 1 line per millimeter on the camera phone. So it's not a very good thing if you're trying to take an important picture of anything. Now, you've seen very often with people with video cameras, everybody has one now, of course. Okay, what this is a low-light video camera, much more sophisticated than any of your $1,000 video cameras you can go out and buy in regards to low light. And what I use it in astronomy for a number of things because it's so sensitive. This video camera, which is this little black part, I can't switch back and forth here. I'll talk about that in a second. It's a PC-164. Let's put it this way, it's 30,000 times more sensitive than your $1,000 video camera you can go buy in low light. And of course, it also has this is just a $10 lens on it, very expensive lens in the past, but nobody uses video cameras with lenses on them anymore. And this blue thing is a modification I've done to the camera. But what you can do, what I want to show here, is the fact that with a lens, you can see that I can blow this thing out because this is running 30 frames a second, 60th of a second exposure. This camera can see in the dark, not in infrared, in just ambient light. It's very, very sensitive. But what I wanted really to demonstrate here was this. Oops, what are we in the way here? Okay, look at the wall over there. See if I can get this lined up here. Oh, you can't look at the wall, you got to look up here. Let's find a place here. Okay, this camera is also very sensitive to infrared. That's why the spot appears a little bigger than it does up there because of the infrared sensitivity. But what I wanted to demonstrate was, let's say you take a video camera outside and you're looking at, you take it and you point it at a bright star, And of course, you're jiggling around, and you see these videos all the time that show this. And somehow, now they think this is an alien spacecraft because it's moving around, and it's actually the video camera moving, of course. But worse than that is you'll see this. Now it's out of focus. And what happens is you get a diffraction pattern created, and you wind up with a dark disk in the center when it's, oops. Here we go. And you see now you get this strange effect. Now you're actually, let's see, let me open up the, we don't want the aperture set down. Let's see here. One of the problems with sensitive cameras is you gotta, oops, and I managed to lose my object here. Where'd you go? There. Now you see, I wanted to demonstrate, you see the difference between out of focus and in focus. But furthermore, you're seeing something else here. You see all this twinkling effect in there. Some of that's caused by the laser, but to be honest, some of it is actually turbulence in the air between here and the laser. You're actually seeing the turbulence in there. And of course, this is much worse if you're looking at a star in the sky. You get this twinkling effect, and people very often think this is a UFO signaling to them. I can't imagine why, but you can see if you do this, the effects you get, then people don't understand that optics can cause all kinds of strange effects. And of course, then you wind up seeing this, and that's the UFO moving around. And of course, it's not. Okay, and you see this is the camera. This is another camera with a lens on it. And this is the modification I did to it. This is the SD 600 Canon camera. Anybody know what this is? What? It looks like an LED light, but it's not. These actually are LEDs, but that's not its purpose. That's to indicate something. It's an infrared illuminator. And you see this on television all the time on the History Channel and Discovery when these ghost hunters run around, don't know what they're doing. They don't use a thermal imaging camera because they're very, very expensive. What they typically use is some video camera, and then they illuminate the darkness with a infrared illuminator. Now, this camera, as sensitive as it is, if you turn the camera on in a cave with no lights on, you're not going to see a thing. You're not going to see a thing with an infrared camera either, unless there's a temperature differential. However, you turn this on, and it's a floodlight in infrared. You can't see it, but this camera can, and it lights up the sky. Now, this is not very handy for lights in the sky and UFOs, but I thought I'd throw this in here because it's how these people use this kind of equipment all the time and misuse it. But it's quite spectacular if you turn one of these on. This, by the way, these are made for security purposes as well as this, for outdoor security purposes, and that's why they're so sensitive to low-level light. Okay, I wanted to show you WWV radio signal because time signals are very important. However, I can't get WWV in here. By the way, anybody tried their GPS in here? They don't work in here either. So it's handy to have a stopwatch. For those of you who don't know, your eye is segmented into rods and cones, and the rods are more sensitive to low light. The cones are color vision. We'll talk about that a bit in a second. And so when you go out at night, it's not a good idea to take your brightest flashlight and take your star chart and shine it on it, because then when you turn the flashlight off and you look up at the sky, you're not going to see anything. And that's because you actually bleach the chemicals in the rods out, and you can't actually see anything anymore until your eyes dark adapt, which can take anywhere from about 10 minutes if you're young to about 30 minutes if you're old. Another thing that goes bad when you get older. So what you should do is either get some red cellophane or some of this stuff, which is much better. It's actually called red stuff. And put over the front of your flashlight, because your eyes are not as sensitive to red light. So when you shine that red flashlight on your chart, it's not going to affect your dark adaptation nearly as much as if you shine a white light on it. Also, it's handy. Here, I'll just pass this around so you can look. This is much better. This is actually designed to be at a specific wavelength for your eye to block the most damaging light to your night vision that there is. It was specifically made for that. Okay, when it comes to time, there is no daylight savings time in the sky. So be very careful when you're setting things and doing time. Oops. That you understand what time you're using. And it's a much better idea to use universal time. Now, there's all kinds of time. Everybody has one of these watches, I assume. What is this? This is not time. This is an abstraction of time. Time is a dimension. Time is flowing through this room right now. This is an abstraction of that so that our puny little brains can sort of follow one moment to the next. That's how it works. But at any rate, there's all kinds of time. Mean time, standard time, Greenwich Mean Time, universal. Sidereal time is the time in the sky. That's when the right ascension of the sky is on the meridian. That's what sidereal time is at that moment. You can actually read it off of those planispheres. But let's talk about universal time. Universal time is sort of the same thing as Greenwich Mean Time, but not exactly, but the difference is not important. What it is, in the case right now here in Las Vegas, it's 7 hours difference from universal time. So right now, you add 7 hours to your watch time, and that would be the time in 24-hour clock, and that would be the universal time. Why is that important? Because when you put universal time in, it's the same time all the way around the world. So you're talking about the same time. You don't have to worry about time zones, and you don't have to worry about daylight savings time. Also handy to have a rangefinder. And if you're going to use instead of latitude and longitude, and I'll pass these around. Remember, this is a 1 to 250,000, and the others are 7.5 minute geologic survey charts. These do not read latitude and longitude. Why they did that I won't get into. I don't agree with why. But what you have to do, if you want to read latitude and longitude off of one of these, is actually draw the latitude and longitude lines on yourself. And then you can take various devices to measure latitude and longitude. But this has that universal coordinate system, the 60 zones around the world, 6 degrees each. It has an obscure thing, and if you see the numbers along the edge of the chart, that's what that is. That's not latitude and longitude. The only place that latitude and longitude is on a standard chart, U.S. Geologic Survey, is in the corners. And then every 2.5 minutes, they mark it on the chart. So, and I'll pass. This is a protractor that you can use to, and if you want a detailed location of someplace, this is the way to do it. This is a 250,000 scale chart of Las Vegas area. I'll pass this around. You can take a look at it. It's not as detailed, but of course it's a much bigger area. It takes 58,000 of those to cover the United States. So if you're interested in this, I'll talk about how you can get this online, or you can buy a program. These things have gotten very expensive. They used to be $1. Now they're about $10 or $12 to buy. So if you buy very many of them. But they have computer programs that will print them up for you too. But also, they have all kinds of strange nomenclature on here. So they make a little symbol device to figure out what symbols are on the charts. Okay, let's talk about a little bit of knowledge on some of these ideas. Magnitude scale, constellation, scintillation, and seeing, I sort of talked about. Some atmospheric mirages and illusions. Okay, some of you have probably heard the term lux. Magnitude, of course, is almost exclusively used in astronomy. But I want to tell you why you should use magnitude and not lux, because this is the definition of 1 lux. It's the illumination produced by a luminous flux of 1 lumen uniformly distributed over 1 square meter. Now, how many people here can tell me what that means? Even the physics people. Well, maybe. There's somebody in here. Well, now we have to know what is 1 lumen. Well, this is what 1 lumen is. It's the luminous flux emitted in a solid angle of 1 steradian by a point source with an intensity of 1 candela. Now, how many know what a candela is? This goes on and on and on. And this is why I stay away from lux. Although this camera, this video camera, your typical video camera is about 3 lux, low light sensitivity. This camera is 1/10,000th of a lux. Okay, if you want to know this in sort of this, Polaris, which is a 2.02 magnitude star, at the surface of the Earth has 4,000 photons per second per square millimeter. Your dark adapted eye is about 28 square millimeters. The shutter time on your eye is about 1/10 of a second. So you can do the calculations here and figure out that 1 lux is a 4.2 magnitude star in an 8-inch f4 telescope. Now, I'm sure that means a lot, people in here, unless you're an amateur astronomer. So let's get away from luxes. Magnitude. Much easier system. It was actually developed thousands of years ago, and it was codified when all this got codified in 1930. Basically, what we do in astronomy is we say that we use a brightness scale called magnitudes, and each magnitude is a 2.5 step, 2.512. As a result of that, 5 magnitudes difference is a difference in brightness of 100. So remember, this is not linear. And we set Vega at 0 magnitude. High magnitudes are faint, minus magnitudes are bright. So remember that. Sort of goes reverse. And we set Vega, the star Vega, at 0 magnitude, which was real nice because we thought Vega was a nice, stable star. Unfortunately, it's not a nice, stable star, and it changed brightness on us after they set the scale. We sort of still use Vega, but you'll see here, now Vega is plus 0.03. Now, here's the magnitudes in the sky. The sun sort of doesn't count. The full moon is minus 12.92. Iridium flares, who knows what an iridium flare is? Okay. There's a bunch of satellites that were put up years ago for satellite military communications, other things, sort of in the beginning of cell phones and stuff. They're still up there, but they have these very interesting panels on them. They're incredibly bright. When the satellite gets just in the right position for about 10 or 20 seconds, it will light up the sky. Way brighter than any of it's minus 4.89. It's, you know, it's like 100 times brighter than Venus. Now, it only lasts a few seconds, but it causes UFO reports all the time. International Space Station, minus 5.9 at its brightest. Now, remember, in these right here, they change depending on the distance and other things. Jupiter, Mars, the brightest star in the sky, Sirius, minus 1.47. The faintest star you can see is about plus 6.5 on a really dark sky, not here in Las Vegas. Get out way out in the desert. And then fireballs are very, very bright. Fireballs are the brightest thing in the sky, except for the moon and the sun, and sometimes they're brighter than the moon. I have seen fireballs. We usually define fireball at minus 5, about the brightness of Venus, up to the brightest one I've seen is minus 17. And if you see one brighter than minus 17, it's too late. Because that means some fragment of an asteroid is coming in. But they can be quite bright. This is what a fireball looks like. It's kind of hard to describe if you've never seen it. Fireball is simply, or bolide is simply a very, very bright meteor. Most meteors you see in the sky are about the size of a grain of sand. Now, how can that possibly be seen? Well, you're not seeing the grain of sand. That grain of sand is moving 20 to 50 kilometers per second when it hits the atmosphere. And as it goes through, it literally vaporizes and ionizes, and it ionizes the particles for about a kilometer or two around it in that streak, and that's what's glowing, and that's what you see. A fireball, on the other hand, is a big chunk of rock, much bigger than a grain of sand. And why it's called a fireball very often is because it seems to have fragments coming off the back of it like a fire. And of course, this is just little pieces of rock breaking off and the ionization around it. And they only last, maybe 5-10 seconds at most. But, this one's minus 13. This was brighter than the full moon. So it really gets your attention if you're standing out there in the dark sky and all of a sudden, for 10 seconds, this thing crosses the sky. Okay, constellations. We have Ptolemy to thank for constellations. He sort of took the old Greek mythological characters that the Greek constellations were on, renamed them in took the Greek myths, renamed them in Latin proper names, and created them. But in 1930, the International Astronomical Union codified all this and then put some constellations, 88 constellations in the sky now. And they're all vertical lines of right ascension and declination now. But Ptolemy, of course, is famous for another thing. He created astrology. Okay, everybody can see this as a scorpion, right? You have to stretch your imagination to see. This is, a chart of it, and this is an actual photograph. And you can see this is Antares, a red giant here, star. Very, very big star. If you stuck the sun in the center of this, the Earth would be inside the star in its orbit. It's a big star. And you can see this is sort of the head of the scorpion, and this is the tail, but it takes a little bit of imagination to come up with. And of course, related to astrology, this is the ecliptic projected in the sky, and you see these 12 constellations, which, of course, astrologers call signs. Actually, there's 13. Ophiuchus is on here, but it's right in here, but they neglect to point that out. And of course, it's because of precession, it's 2,000 years out of whack. So wherever your sign is, it's off by one. Astrologers never talk about that. And of course, here's, the nice medieval depiction of all of this. You can see here's Cancer, Gemini, Taurus the bull over here, Pegasus a flying horse. And you can see this is more art than it is constellation. This is Orion here. Here's the, you notice here, this is Betelgeuse and Rigel. The stars, proper names are Arabic. The constellations are Greek mythology and Latin names. Why is that? Well, the Arabs navigated across the desert, and navigating across the desert is just like navigating on the ocean. So they named all the bright stars, about the 300 brightest stars in the sky. And Betelgeuse means armpit in Arabic, and Rigel means foot in Arabic. And you'll notice where Betelgeuse and Rigel are. Okay, let's talk about seeing, this turbulence atmospheric issue here. In astronomy, we tend to lump scintillation and seeing all together. We call it seeing. And basically, it's a blurring and twinkling of stars, which cause all kinds of people to think that stars are UFOs. And basically what it is just a changing wavefront at 5 to 100 times a second. This is very rapid. Due to the varying densities of temperatures and densities in the atmosphere, as the light passes through it, it gets refracted around. This can fluctuate up to 2 to 3 magnitudes. You can have a fairly a fainter, if it's not a steaming bright star, just disappear because of this for a few seconds. It moves up to 20 times its own diameter. Its size can go up by a factor of 20. Its shape changes. And more importantly, because of the dispersion of the wavelengths, the color changes very rapidly. It goes red, green, blue. Now, all of this has more of an effect near the horizon, basically close to, from the horizon up to 20 degrees. But it happens all over the sky. It's just more apparent lower down in the sky. And it happens to planets as well. The old saying that planets don't twinkle, not true. However, the seeing has to be particularly bad for planets to twinkle, but they do twinkle. So let's talk a little bit about atmospherics. I'm going to talk a little bit about mirages and sundogs here. And of course, how many people have ever actually seen St. Elmo's fire and ball lightning? Pilot. Yeah, if you fly, you see all kinds of things. I'll never forget the first time St. Elmo's fire engulfed my airplane. If you were religious, it would change your attitude, but of course I wasn't. But it's very interesting. But ball lightning, the first time I ever saw ball lightning was I was flying in pilot training at night, and ball lightning attached itself to my wingman's pitot boom, and then rolled down the pitot boom into the cockpit with him, where I thought he was going to die, and I mean psychologically, not literally from the ball lightning, and then it exited the aircraft. And we were only flying 600 knots at the time, so it can get your attention. Of course, in the atmosphere, you have all kinds of things going on with water vapor, dust, ice crystals. These all cause various effects when you got light shining off of them, either the sun or the moon. You can get coronas and glories and all kinds of other things. And these cause once-in-a-lifetime experiences for people. How many people have ever seen a glory? Okay? If you're flying in your airplane and you have a cloud layer not too far below you and the sun behind you and you're looking down like this is what you'll see. You'll see this rainbow effect around you, and it will center on you. If you get up and go to the back of the airplane and look at it, it will center on the back of the airplane. And it's centered on your viewpoint. And this is often called in flying pilot bows. But I don't know this for sure, but it's my speculation. Remember all the medieval art with the saints and everybody with the halo around their head? Think about where all those people stayed. There were monasteries on mountaintops with lots of fog, and they go out in the morning, and the sun be behind them, and there's their head right there, and this is around it. Okay, we have all kinds of mirages that cause various effects. You can see various mirages. There are hundreds of different types of mirages due to temperature inversions. They almost always occur very close to the horizon, and you get weird effects here that people all the time think are alien spacecraft. This is one that just appeared just a few days ago. This is the actual sun setting. This is a mirage, this is a mirage, this is a mirage. In fact, what you have here is three mirages blended together. This sort of explains what's happening here. This is the descending mirage, this is an ascending mirage, this is an erect mirage going the other way, and then it combines to form this. This causes all kinds. I don't know why people think this is a UFO, this is a UFO, and this is a UFO, but they do. It's merely, this is a halo, a periarc, sundogs here, solar pearl here, and you can actually see in this one, because there's lots of ice crystals in the air, you can see sort of the scattering here that you get out of it. Now, even skeptics might think this is a UFO. This is a very rare phenomenon that nobody quite understands why it happens. But this only lasted 60 seconds. And happened to be actually an Air Force guy who photographed it. He saw it, grabbed his camera, and this is actually the way it looked over the course of 60 seconds. This is one more recently. But this happens, and this is probably something similar to this is what happened in the Chicago O'Hare UFO case. That is a cloud. But you have to admit it's an unusual cloud. So in aeronautical, if you were out at night and the moon was up and this F-22 flew by with a bow shock, and this was all that was illuminated, what do you think you would see? But this causes as many UFOs as anything else. These high-altitude balloons, they go up to 100, 120,000 feet. They're incredibly bright. They're much brighter than Venus. They're usually launched at sunrise or sunset, so you go out and you see this bright object in the sky. What's worse about them is they get up there and they hang there for a while, and then they explode, and they instantly disappear, which makes it even more mysterious. Okay, a little bit about vision. We all like to think that our eye is sort of like a camera and records accurately. It does not. All kinds of funny things happen with vision, both in how our brain system tries to correct things. The human eye is not very good. The brain tries to fix it, and sometimes it fixes it wrong. And so we have things like the audiokinetic effect. This plays in. If you've ever stared at a very, very bright object, it will start to move. Not scintillation, it's moving because of scintillation, but it's moving also because it appears to move, and it's because your eye is moving. And you don't realize it. Your eye starts dancing, and the object starts dancing in the sky. And of course, you have all these other kinds of funny things that happen with vision as well. The eye is pretty complicated. In fact, these cells right here, we now are beginning to think or actually act just like brain cells, actually process information here, not just record it. And this is the rods and the cones here. Interestingly enough, you'll notice the light comes in here, goes past all of this, and comes back onto this. Now, here's a cute trick when people talk about color. We talk about color vision here. Everybody, except for the people, I'm not talking about people who are colorblind now. Color is an illusion. It's not real. Take a look at that laser right now. With the system, the way your eye works, you should not be able to see that in color, because that's a monochromatic color. Your eye can only see by comparing various cones to each other, and there's no light in the other cones. And it's because it does this. This is where your rod sensitivity is. This is your various cone vision down in the blue, the green, and in the sort of yellowish. Now, how the hell you see this up here is bizarre. But the bottom line is, in order for you to see a color, you've got to compare two of these against each other. Well, if a color is pure, then you can't compare. So what happens is your brain sort of makes it up. It says, I got to stick something over there to guess. Very often it guesses wrong. I could show you two pure colors in here, and you would say it's a particular color, and you'd be wrong, because your brain screws it up. And so it's an illusion, it's an adaptation that we have so we can distinguish things. The key to it is, if, say, this right here, if I change the intensity of this, even though it's a pure color, the color changes, at least your eye. The color up there, the monochromatic wavelength doesn't change, but how you see it does. So it's an abstraction of reality. It's basically a constructed guess. The one thing your eye does do well is it has high dynamic range. Yeah. It's the optical system's very poor. It's low resolution. The brain fills in for the edges, has severe chromatic aberration and severe astigmatism. So it does do contrast, edge enhancement, and color fairly well. It makes all these mistakes in perception, omission, various things that it does. So let's talk a little bit about some illusions here that are related to vision and the way the human brain works. The moon illusion, which I'm sure you've all heard of, is the moon appears larger when it's rising, right on the horizon. And this is true of everybody. It's actually 1.5% smaller when it's on the horizon because it's more distant than when it's overhead. It's, you know, half the diameter of the Earth away, more distant. So what happens is the moon actually does change in size by about 11%. But if you look over here, which of these orange circles is bigger? I think everybody probably sees this. They're exactly the same size. Exactly. Now, I suspect almost everyone in here, maybe somebody can force it, but sees this as larger. It's not. It's the same size. Now, what's going on with this illusion, we think, is the fact that when an object is silhouetted against smaller objects, it appears bigger than when it's silhouetted against larger objects. So as the moon rises, it, even though it's staying the same size, it appears smaller because it's not silhouetted against anything in the sky. Which monster or alien is bigger or larger. They're exactly the same size. Exactly. It's because of the perspective, and our eye just thinks that in this kind of perspective, something like this is going to be larger than this. A wonderful illusion, the water's running here, down, and then it's going back uphill again. Try to force yourself to figure out what's wrong with that. Exactly the same size. But when you put the perspective this way, they change. How many have ever seen this checkerboard illusion? This, A and B, are exactly the same grayscale. Can any of you see that? Well, you might not believe me until I do that, or until I cut them out. But they are. This is my famous, most interesting one. The rotating snakes. Look right there, stare right there, and you will notice that it starts rotating. And then if you stare right over here, you'll notice that it starts rotating. There's nothing moving on that screen. Nothing. It's all being done by your brain. Stevensville lights, I'll just mention quickly. Here's Stevensville, Texas. This is the MOA. Not a single person apparently in Stevensville knew these MOAs were here. And what happened that night in the Brownwood MOAs is 8 F-16s were flying in there, dropping flares, and did afterburner climbs out of there, and these people saw this and thought it was alien spacecraft. And this is the kind of flare they were dropping, as I was telling you about. This is what it looks like. It's very high illumination flare. I don't know how many people have ever seen an afterburner on a fighter jet at night. It's quite spectacular. This is in the daytime, of course. But afterburner, you're just basically dumping fuel into the exhaust of the aircraft to give it a kick, and it does give it a kick. You don't do it very often because it burns a lot of fuel. But this flame can go out 150 feet behind the aircraft. And at night, it's spectacular. And unfortunately, that night, all 8 F-16s did an afterburner climb out of the area. And, of course, the people in Stevensville went nuts over it. Now, experience, I can't give you any experience. But what I suggest to you is you go out and you look at planets, you look for twinkling and scintillation effects, you look for iridium flares. I'll tell you how you can do that. And if you live near a military area, you go out and look for flares. Here is a couple of websites. If you're interested in fireballs, these two will tell you if there's been a fireball occurred recently and where at. United States Geological Survey, this is where you can get the download of the topo maps. I caution you though, it takes 9 regular sheets of paper to print one topo map, and they're 54 megabytes to download. Here's Heavens Above is a very good site because it has a lot of astronomy, time, and satellite data. If you want to know where iridium flare is, look up on today, put your latitude and longitude in there, look up, and it will tell you all the satellites that will pass in your sky tonight and their altitude and azimuth when they appear and disappear. And so it's very handy, and it tells you when the iridium flares are. So you can just look it up here for your particular location, go out and look at that part of the sky, and then you'll see the iridium flare occur for 10 or 15 seconds. I handed this out to you in one of the handouts. You see here, there's a couple of books for astronomy I recommend here. This is a wonderful book on mirages, an older book, but on light and color in the outdoors, this rainbow book. The only UFO book I've ever recommended, written by a believer who became a skeptic for life after he did this research project. And then here's a couple of books on vision that I recommend. I have to say this every time somebody talks about lights in the sky. Aliens travel here thousands of light years to get here. Then they employ stealth technology so we can't see them on radar. They employ sound dampening so we never hear them. Then they employ some kind of energy mass so we can't see their electromagnetic radiation from all this energy they're putting out to get here. So nobody can see or detect them, and then they turn their lights on. That makes a lot of sense. Well, whether extraterrestrial life exists or not is a very compelling question. We simply do not know the answer. Maybe someday we will, but we do know there's no evidence, and we do know if you just do a little bit of physics, it would be very, very hard to travel between the stars. Not impossible, but very, very difficult. I don't know if we can tonight. If anybody's interested, at 9 o'clock tonight, I'll be at the front door if it's clear, and we can go out and look at some things with lasers. During the conference, when I'm not in talks, I'll be at the CSI table if you want to come by and ask any questions. Just remember, we are nothing but animated stardust. Thank you very much. Almost always turn out by most people to be UFOs. They don't understand what they see. And furthermore, it's not just that they're UFO. UFO means unidentified flying object. It was a phrase or an acronym coined in the early 1950s to explain something that was unexplained in the sky, but it has become to mean, that is, an unknown means an alien spacecraft. Today, people, when they see lights in the sky, do some very bizarre things. It changes their lives. People quit their jobs and devote themselves to UFOs, and this is more than just a few people doing this today. There's a very famous doctor in Phoenix during the Phoenix Lights who quit her practice and started making UFO movies over the Phoenix Lights. Now, what are lights in the sky? By and large, for most people, when they go out and see lights in the sky, they're misidentified, misinterpreting, misperceiving, misjudging, misunderstanding, and unfortunately their whole belief system is overriding all of this, so automatically it becomes an alien spacecraft. Now, a little quick thing about me. Yes, I was a bit younger here. I'm a retired Air Force pilot and an astronomer. I held a top secret SCI security clearance, which is somewhat relevant to today's talk. I have worked and flown in Area 51. I have it in quotation marks because the Air Force has never called it Area 51, ever. It's called something else that's classified. So I'm speaking only for myself because the Air Force is very sensitive about this subject. They don't want anybody to talk about it. And since I am a retired officer, I always put that disclaimer in there. I have observed the sky. I've got over 40,000 logged hours of observing the night sky, thousands flying, thousands observing the sun, thousands observing atmospheric phenomena, and in addition, I've logged over 3,000 parachute jumps. As you see, the sky has been a big part of my life. This is some of the things I've seen. Thousands of fireballs, and we'll get into what that is later, hundreds of satellite boosters and reentries, hundreds of different types of mirages, atmospheric lensing, flares, ball lightning, St. Elmo's fire, dozens of skyhook balloons, and yes, I have actually been struck 7 times by lightning. Now, some people say that explains the way I am, but I will let you be the judge of that. Reports. When you have the public reporting lights in the sky, typically you have 3 categories here: the honest report, the exaggerated report, and the hoaxed report. The honest report is someone who honestly is trying to explain what they saw, but they're almost always wrong. it's just so easy for people not to understand what they're seeing, having their overriding psychological and sociological issues influencing what they're seeing, their lack of knowledge, particularly of astronomy and angles. You'll typically see people say, it was moving 3,000 miles an hour, it was a mile in diameter, and it's a mile away. Now, none of those are knowable. You can't possibly know that. They're just making it up because it's what they think it should be. And they're reporting totally out of context. And of course, a lot of times when something pops up, it surprises people, and that influences how they see something, particularly if it's something they've never seen before. Now, of course, you have the exaggerated report where somebody at this point is trying to throw their opinion in there and exaggerate what they actually saw. Again, it's very inaccurate. It's an embellishment. It's not technically a lie. It's more of a tall tale. And then, of course, you have the hoaxes. They're just lying. And today, most hoaxes are actually created in Photoshop and After Effects, unlike in many years past. But the ones that are actually in the sky tend to be road flares hung from helium balloons. This is incredibly stupid and dangerous to do, but people do it all the time. Everybody knows that After Effects is the video version of Photoshop for video. Before I begin here, I'm sure all of you have heard about the end of the world on December 21st at 11:12 Universal Time. Anybody not heard about it? Does anybody think the world's going to end? It could. I mean, an unknown asteroid could pop up and hit us, but I think it's highly unlikely. What this is based on, in large part, is the winter solstice. People think about it as a day. The winter solstice is not a day. It's an exact moment in time when the sun reaches in the northern hemisphere, when it reaches its greatest southern longitude, 120 angstroms, or 532 nanometers. I hate nanometers. Any rate, but what it does is it takes an infrared beam, twice that, and pulses it. Now, why is that important? It's important because if you have one of these, and it's a cheap one, it's dangerous. Not because of shining in your eyes, that's dangerous to look at. Why? Because if this doesn't have an infrared filter on it, you're looking at infrared radiation, it can damage your eye, and you will never see it. So if you have one of these, make sure it has an infrared filter in it. Okay. The sky is filled with all kinds of objects. And of course, historically, people thought of the sky as being very mysterious. All these lights in the sky, they didn't understand what they were, heavenly substances and various other things. And as a result of it, in ancient times, they viewed the sky as having gods in the sky in various forms and other ways. Today, many people sort of bridge this gap by sticking this in the middle, an alien spacecraft. So, this magical sky is very distant, and this is even to people today, untouchable, not controllable, powerful, filled with darkness and fear, and people are looking for meaning in anything. And of course, historically we had the gods and the myths, more recently astrology, and of course today UFOs and aliens. Now, very often people will talk about this idea. When I'm on television a lot, they ask about this all the time. The trained observer. Who is trained to look at the night sky, or in the daytime for that matter, and identify what is there? And what kind of training do you get for this, and what do you observe? Well, in popular culture, this is meant to be some person who's trained to look and observe accurately at the sky, and is typically described or promoted as the idea of being pilots and police officers. And lots of people think they're incredibly credible. We have a few pilots in here. When was the last time any of... A little bit later. But let's talk about galactic alignment. Back in 2003, when Planet X was going to come by the Earth and tilt the axes, not the magnetic axis, the real axis of the Earth, I offered this wager that if anybody wanted to sell me their property at 10 cents on the dollar, I'd be happy to buy it. Because if the world was ending, they really didn't need it. I did actually have a few people take me up on this. We can talk about their judgment, but... Okay, let's talk about this. This red line here, it may be a little hard to see, that is actually the ecliptic in the sky. This is a star chart from a program. This is the sun right here. And what you're seeing is the sun always moves along that line. You can't get off that line because that's a projection of the Earth's orbit as we see it. Now, where's the center of the galaxy? The center of the galaxy, this is for December 21st at 11:12 Universal Time. This is the center of the galaxy right here. It's 5.5 degrees away. So it's not lined up, so you don't have to worry about the world ending. And of course, right here is the center of the galaxy. Everybody recognize it? I took this image a few weeks ago. I'm going to have to step back here a bit. The center of the galaxy is right there. It's Sagittarius A, and there is indeed a 4.1 million solar mass black hole there, but you can't see it because there's so much dust obscuring between us and the center of the galaxy. And I want to show this as an example because there's something called a window that's about 4 or 5 degrees away from here that I took a picture of to show you an example of how much difference the dust makes. There are about 15,000 stars on this picture. It's about 3 degrees by 2 degrees wide, taken with a Canon digital single lens reflex on a astrograph. But this is only 5 degrees away. And I don't know if you notice the difference. There's 15 million stars on this picture because the dust is not obscuring it. You see some of it, the dust is in here obscuring that area. So here's the night sky. I was hoping if it was clear, but I don't think it's going to be. We'll go out, I'll talk about that later, and use some lasers and look at the night sky. By the way, how many people own one of these green lasers? How many people know how they produce their light? Physics people? What's the wavelength that this produces at? The wavelength you see over here on the wall is 5,300 along the ecliptic. The ecliptic is the projected plane of the Earth's orbit, which is tilted 23.5 degrees. And so when it reaches that moment, that time on that day, on 21st of December in the northern hemisphere, that is actually the winter solstice. Now this is all fairly complicated because we base our time on the sky. And that's based on the Earth's rotation, both on its axis and around the sun. And it's not consistent. It's not exactly the same all the time. And things change. The Earth wobbles on its axis in a 26,000-year period. And so what happens is the sky changes over that period of time. This is also why astrology doesn't work. And here's just some of the parameters on the Earth's orbit. You know, you will notice here that, in fact, the closest approach to the sun is January 3rd. The furthest away from the sun is on the 4th of July, and this is the greatest elongation of the ecliptic here. And the actual orbit of the sun is, you know, varies plus or minus about 2.5 million kilometers. So, and then you have all this kind of stuff, how we measure the year. Astronomers use this, but you can go from perihelion to perihelion or equinox to equinox. So what about the end of the world? Well, this all started about 10 or 15 years ago when some people sort of looked at the Mayan calendar and all of a sudden realized that it was going to end on December 21st. Just like our Gregorian calendar ends on December 31st. But the world doesn't end every year. So this, of course, is a bunch of nonsense. The Mayans basically had no mathematics. They could count, and that was about it. And they had this long count for their calendar, and it does indeed, if you read some of the records correctly, end on around the 21st of December. There's lots of New Age beliefs about this that have nothing to do with anything. They just want to believe the world's going to end. The galactic alignment is what I'm going to speak about a little bit here. And, of course, Planet X, there's this idea that somehow this rogue planet is going to fly through the inner solar system and disrupt the Earth. And, of course, there's no such planet. Doesn't exist. And geomagnetic reversal, this is something that could actually happen. It's not likely to happen on December 21st, but it will cause a lot of havoc, but it won't end the world. And I'm going to talk about this a little bit because of what's happening to the magnetic pole of the Earth.